Okay, so it's 4:10. We have a few people here, so that's good. So sorry I had to change the time, but I'm glad that some of you made it, so that's good. Hopefully other people will look at this once it's not live. That will be good too. So I got a few questions from email. So let me just see if I can pull that up really quick. And I also, so up on the screen right now are the four kind of main topics that we covered since midterm 1. So we talked about correlations, we talked about paired sample t-test, and we talked about one-way ANOVAs and factorial ANOVAs, which are just a little more complicated versions of one-way ANOVAs. So we'll talk about this kind of stuff, and then questions as they come in we'll answer. So I'll start with some questions that that I got from email from Manuela. So she has a few questions. So the first one is, when do you use the Tukey test? So let's jump right in. So if questions come to you and you're watching, you can put them in the live chat. If you have a question but you're not watching, you should email it to me. And if it's not in the video, then I'll try to answer it in text when you email me. Okay, so Tukey's honest significant difference. Tukey, this is some guy, something Tukey, honest significant difference. So here is where we want to see which means are different in ANOVA. So this has to do with ANOVA. And this could be either one-way ANOVA or factorial. Okay, so this is what we're working on. So let's say you have a hypothesis, and that is that grade of education will predict height. And so what you do is you measure first graders, you measure second graders, and you measure eighth graders. So you measure the student's height in each of these 3 grades, and then you plot them out. And you see that you have a distribution of heights for your first graders. You have a distribution of heights for your second graders, and then you have a distribution of heights for your eighth graders. So if you were just to plot their heights in a graph, where this is where your y-axis is just frequency, how many students have that height, then you would see something like this. You'd have one distribution for first graders, kind of an overlapping but a little bit higher distribution for second graders because maybe they're a little bit taller, and then you have this distribution for eighth graders out here. So you calculate your sum of squares, you calculate your mean squares between and within, so you get f, right, is your mean square between divided by your mean square within, and that equals 20, which is significantly different than your critical value. It's bigger than your critical value. So you would reject the null hypothesis. You would say, okay, grade seems to predict height. You have a difference in you have different means. Oh my God, I'm getting so many emails now. Good, very good. We'll go through all of them. So you get a significant f value. You would say that the means between these grades are not the same. But that's all that tells you. The means between these 3 grades are not the same. So you need to say then, okay, well, which means are different from the others? So you need to say, okay, are second graders significantly taller than first graders? Are eighth graders significantly taller than second graders? And are eighth graders significantly taller than first graders? So here is where you would calculate the Tukey's HSD. So remember that the Tukey's HSD is the critical value for this. So it's like crit HSD, which you get the book out of the book, and it's usually at off of 0.05 times, I'm running out of space, so I'll put it down here, the square root of the mean square within divided by little n. So what this is telling you, this will give you some number. Let's say it's 4.5. And remember that the unit of this is inches. So that's what you're measuring. So what this tells you is that these two means have to be at least 4.5 inches apart for you to be able to say that second graders are significantly taller than first graders. And this has to be at least 4.5 inches to say 8th graders are significantly taller than second graders. And then this difference from first to 8th has to be at least 4.5 inches as well. So you use Tukey's when you have 3 or more groups after you find a significant F value. So you do your ANOVA, you find a significant difference, which says that, let's see. So your null hypothesis in ANOVA would just say your first mean equals your second mean equals your third mean. So when you reject that, you're saying, no, these means are not equal. You use Tukey's on a significant difference to then figure out which means are different from other means. So like you would subtract this mean from this mean. That would get you some distance, some number. Let's say it's 3. So 3 inches difference in height. Tukey's HSD says it has to be at least 4.5 inches for them to be far enough apart for you to say that they're different. So in this case, these two would not be different. You subtract 8th grade from 2nd grade, you get a distance like 9. 9 is bigger than 4.5. So you would say, okay, 8th graders are significantly taller than 2nd graders. You do the same thing for 8th graders and 1st graders. You find a difference of 10. 10 is bigger than 4.5. So you say 8th graders are significantly taller than 1st graders as well. So that's Tukey's HSD. So you remember, you only need it for 3 or more groups. You could do it for 2 groups, but if you find a significant difference with 2 groups, you always know that they're different from each other because there's only 2 of them. So like if it was only 1st and 8th graders, and you did a t-test, because that's what you would do, you have 2 means, you do a t-test, you find that they're different, you don't need to do a Tukey's because you know that there's only 2 groups. You know that distance must be significantly larger than what Tukey's HSD would calculate, which is true. So 3 or more groups is when you use Tukey's. I'm getting lots of emails. I feel it buzzing on my phone. So we're going to work through them. Michelle Goldberg, I see your email as well, so we'll go through that too. So, okay, let's keep chugging through the questions. So that's HSD. How many Fs do you calculate for a one-way ANOVA and for a 2x2 ANOVA and a 3x3 ANOVA? Okay, this is an easy one. So, how many Fs do you calculate? You calculate Fs based on the number of IVs you have. So, in a one-way ANOVA, you only have 1 IV. So, like the previous example was a one-way ANOVA. It was that grade predicts height. So, our IV was grade, and it had 3 levels. Right, it was 1st, 2nd, and 8th grade. And our DV was height. This is just from the previous example. So if you're watching it or you're taking notes, this was what the setup was for the first example. And so the F that we calculate, we have 1 between and 1 within. So here we just have 1 F and 1 F value. Okay. Let's say we have an example like we want to know if, let's say we're measuring antidepressant, and we wonder about both the sex of the person and drug level. So we have something like This will be a 2 by 2, just to show you. We have like male, female, then we have like no drug and drug. So here we have 2 IVs, so this is 2 IVs. So we have sex and drug. And rock and roll. No, not that, just these two. And the DV, in this case, could be like depression. Say we're working on some antidepressant drug. So we know that, on baseline, females tend to be diagnosed more with depression than males. The drug may have antidepressive effects. So we want to know how these both interact on our DV of depression. So here, we're going to wind up having 3 Fs. So we have 3 Fs. 1 for drug. 1 drug. 1 sex. And 1 interaction. Drug times sex. So this gives us 3 F values. Because we have 1 IV, we have the other IV, and then we have the interaction between the 2 IVs. So even if we had something that was more than 2 levels, so let's say we had 3 by 3 ANOVA. Let's go crazy. Let's say we have my squares evenly shaped. Okay, let's say we are testing drug on, let's say age we think has an effect. So here we have no drug, here we have low dose, here we have high dose, and here we have like 0 to 18, these are like our young people. Then we have like 19 to 64, these are like our adult age people. And then we have 65 plus. So we have 3 levels for each IV, right? We have drug up here, and we have age on this side. Age. So here, we would also be getting 3 F values. So again, here we would have, we have 2 IVs. This is age and drug. Our DV again can be antidepressant or just regular depression. And we have 3 Fs. So here we have 1 for drug. These are also called your main effects. So let's say that's what was significant. And you see that, okay, as dose goes up, something happens to depression. As age goes up, nothing happens to depression. And there's no interaction. So like, it's not, so drug going up is not dependent on age. So we have 1 for drug, we have 1 for age, and we have 1 for drug times age. So whenever you have 2 IVs, you're going to wind up with 3 Fs. When you have 1 IV, you're going to wind up with 1 F. The reason why you have 3 is because that third one's always the interaction of the other 2. So that's how you figure out how many Fs you need, is that. Okay. There are lots of questions for this one, so I'm going to try to move through them. I'm not going to try to linger on them for too long. So. And because the more I write, the longer it takes to erase all of it. Okay. So I think we had one more from Emanuela. Let's see. And also, can you go over how to calculate Pearsons R? Okay, Pearsons R. And other people had asked me about Pearsons R as well, so I'll go through an example of that. From the recitation, I'll just walk through one of the recitation examples. So you should also have that handed back. So, okay. So let's do number 2. So this will be Pearsons R. Pearsons R. And this will be number 2 from chapter... Oh, I see. So Michelle, we'll do the one that you want to do because this is actually correlation. So chapter 9 in the softcover book is it's correlation. Chapter 9 is correlation. So let's find in the hardcover book and we'll do that one. So number 5. For me, it's chapter 11. So let's see if it's the same thing. So you calculate z-scores when doing a correlation, but in the end, you're actually making a correlation. It's actually going to be R. Number 5. Okay. I'm going to just change this. No, not number 2. Number 5. And this is chapter, it's 11 for me. So 11 hardcover. 9 soft. Okay. And let's make this a little not as thick because issues. Size. Okay. That should be better. Okay, so number 5. A random sample of 7 junior high students is selected, and each student is given both a math and a spelling test. Their scores are as follows. So we have math, we have spelling, and they each have, there's 7 of them. So there's, these are the numbers. So 15, 5, 16, 10, 11, 3, and 12. And spelling is 13, 6, 14, 13, 11, 5, and 10. Okay, so what's the hypothesis here? The hypothesis is that math and spelling grades are not related. So regardless of what you've got on your math test, your spelling test would be completely different. The alternative hypothesis is that there is a relationship between math scores and spelling scores. So as math scores go up or down, then spelling scores either go up or down. We don't know if they're positively related, we don't know if they're negatively related, but the alternative hypothesis would be that there is some relationship between these two scores. And you can kind of think about how that would be true in real life. So let's say someone who has never been to school before, or someone who's never been educated in school, you give them a math test, they'll probably score low. You give them a spelling test, they'll probably score low too. Or someone who's been to college versus someone who hasn't been, maybe they'll be related. So you can see how this would make sense in real life if these two would be related. So let's test it mathematically and see if it's true. So the first thing you would do in this question is calculate z-scores, right? You want to normalize these scores into one unit. So I'll give you a hint, and not a hint, but the numbers that you have to calculate here, they'll be given to you on the exam. So you first have to calculate, so like first here you need to calculate mu, or your mean, and your standard deviation for each one. This will be given to you. You don't have to calculate this for the test. And then you'll also be given the z-scores for each of them. So I'm just going to make some up because I don't want to waste our review time with me calculating standard deviations, because I think that's a waste of time since you won't have to do it for the test. So I'm just going to figure out some relatively reasonable number that could be the mean, and then standard deviation we'll just guess on, and then we'll move on from there, because I don't want to waste time. So I'm just going to actually calculate the mean, 11, 3, 12, divided by 7. So the mean for this one is 10.3, 10.28. The mean for this one is 13 plus 6 plus 14 plus 13 plus 11 plus 5 plus 10. Whoops. Means also 10.28. And let's see. Oh, you can probably see my cat in the background now. Can you see him? Okay. So which one varies more? Around 10.28. This one goes up to 15 and 16. This one only goes up to 14. So this one's going to have the higher standard deviation. So let's say here the standard deviation is I don't know, 3. Let's say here the standard deviation is 2. These are guesses. I didn't calculate these. So here you would make a z-score for each one. So remember, z equals x, which is your observation, minus your mean divided by the standard deviation. So this is like 5 divided by 3. So I'll say this is like 1.6. This is going to be 5 minus 10, negative 5 over 3, so it's like negative 1.6. 16 minus 10 is like 6 divided by 3. This is like 2. This is like 10 minus 10 divided by 3. This is going to be almost 0. We'll just call it 0. 11 minus 10, this is like 0.3. 3 minus 10, 7, so this is negative 2.1-ish. 12 minus 10 divided by 3 is like 0.6. So these numbers that I'm calculating are going to be given to you on the test. That's why I'm not going hard on these. I'm just going very soft on making these numbers. 13 minus 10 divided by 2, so 3 divided by 2, 1.3. 6 minus 3 is 4. 4 divided by 2, that's going to be negative 2. 14 minus 10, 4 is a positive 2. 13 minus 10, 3. This is like 1.3. 11 minus 10 is 1 divided by 2. It's like 0.5. 5 minus this is like negative 2.5-ish. This is like 0. Okay, so again, loose on these numbers. These numbers will be given to you. Okay. So then what you have to do, this is where the correlation part comes in. Now you have to multiply these numbers together. So here, so this is like zy, and this is zx. So now what we have to do is we have to find the sum of zx times zy. So here's like the part you'd have to start in. So 1.6 times 1.3, calculator. .08. You should wind up with 7 of these numbers because you're multiplying one of these observations by one of these observations. So negative 1.6 times negative 2 gives you positive 3.2. 2 times 2 is 4. 0 times 1.3, 0. 0.3 times 0.5 is 0.15. Let's just confirm that. Yep, that's right. Negative 2.1 times negative 0.5, 2.1 times 2.5 equals 5.25. It's a decimal, non-negative. And then 0.6 times 0 is 0. 1, 2, 3, 4, 5, 6, 7. You have 7 numbers. You did it all correctly. And now, so that is zx times zy. Zx times zy. Remember, z's will be given to you. You multiply them together. you get these numbers. You get one number for each pair of observations. Now you add them all up. So 2.08 plus 3.2 plus 4 plus 0 plus 0.15 plus 5.25 plus 0 equals 14.68. So this is your sum of Zx times Zy. Okay, so now we can calculate R. So give me some space down here. Go into a different color because it's a different step. Okay. So R, or your Pearson's correlation, equals the sum of Zx times Zy divided by NP, which is the number of pairs you have. P is for pairs, number of pairs. We have 7 pairs. So we have 14.68 divided by 7, which is your number of pairs. And that gives you an R of like 2, around 2. So then we would go and we have to find our critical value of R. So which means that we have to find our degrees of freedom. So in this case, degrees of freedom for Pearson's R equals number of pairs minus 2. So here our degrees of freedom would be 7 minus 2 equals 5. So we go and look in the R table in the back of the book, which is table E, and you find that at 5 degrees of freedom, for an alpha level of 0.05, which is what the test asks, the question asks for, is so the crit value is, get down there. So we get 2. Crit value equals 0.75. So our value of R is greater than the crit value of R, so that we would say there is a significant correlation between math grades and spelling grades. And the fact that this is positive says that as math grades increase, spelling grades also increase. So for number 5, math ability is related to spelling ability. As math grades go up, spelling grades would also be predicted to go up. And that's at alpha of 0.05. So that's question 5 from that chapter 11 for correlation. So that's how you would do correlation. Let's check to see if I answered the question in the email. How do you go over how to calculate Pearson's R? Yes, I did. Okay, so just to reiterate, the Z values will be given to you. So you'll get like this column and this column and this column and this column. And what you'll need to generate on the test is basically this. You have to add them all up. You have to do the R. You have to calculate your R, find the critical value, make the judgment call if there's a relationship or not. And then, if they ask you for effect size, it's R squared. So this one is weird because the numbers, like my standard deviation is much, much too big. So I'm getting like numbers that are just too big everywhere. Really, your R statistic should not be greater than 1. If it's bigger than 1, that usually signals that something is wrong. But in this case, with these numbers, that's how it works. So just for you to keep in mind. Okay, so I'll leave that up for a second while I look at more emails so you guys can just look at that and see what I did. Calculate Z, given to you. Calculate the multiplication of Zx times Zy. And then add them all up, divide them by number of pairs, degrees of freedom, number of pairs minus 2, and then find the crit value. Pointer bigger, I can't do. That's just the cursor from drawing. So I apologize. I don't have very technical items so I can't do that. But I will move on from there and answer your other questions. Okay, so remember, a z-test, as we covered in the first part of the class, a z-test compares your group, like your sample, on some measurement to a population when you have both the population's mean and standard deviation. So that's not looking at the relationship between two interval ratio variables. That's looking at comparing one mean of a sample versus one population when you have the population's mu and sigma. So that's a z-test. You do a correlation when you think that two interval ratio variables are related to each other. So could be height and weight, could be number of windows open is correlated with what the temperature is in a room, could be number of pirates in the world and instances of terrorism, if they're correlated. It's just like two variables, two things you can measure. Let's say height of 8th graders and age of parents, if that's correlated or not. Just looking at how two variables that are interval ratio measured, if they're related to one another. If as one moves, the other also moves. Correlation comes from correlated, so how they are related to each other. So Fisher's z-test, paired samples t-test. You use a paired samples t-test when you only have two groups, you only have two samples, and the two groups are correlated with each other. So I will do an example since you're both asking about paired samples t-tests. So let's see. So paired samples t-tests come from chapter 13 in the soft book or 15 in the hard book. So let's look. T-test. So it's just when your two groups are correlated. So that's when you use it. Just like a t-test, but when your two groups are correlated, use a paired samples t-test. A lot of the time, paired samples t-test is most easily recognized when you're doing something longitudinal, like over time. So let's say you are interested in depression or like some drug. So like antidepressant drug. So what you do is you measure depression at time 1 on some like group. Let's say it's like 40 40 college kids. And then you give this drug at some time point, and then you measure depression again afterwards. Now this is time 2 on the same 40 kids. So now you follow up with those same kids after they've taken this antidepressant drug, and you want to see if this is greater than that. Is depression measure 1 bigger than depression measure 2? If this is significantly bigger than this, then that means that your drug had some effect on these kids. So what do? It's basically the same thing as a t-test. You just change one little thing. So remember that a t-test is your t-ratio equals your mean of group 1, so in this case would be time point 1, minus your mean of group 2, which would be your time point 2, divided by the SED, the standard error of the difference. And usually, the SED equals the square root of standard error of mean 1 squared plus the standard error of the mean of group 2 squared. That's how it always used to be. This is for independent samples. Independent, it's not spelled right. Independent samples. So here, they're not correlated. So this is what we did before the first midterm. This is what you did on the midterm. So what's different? What's different is for paired sample, we add into this equation something else. So SED, gotta make this big. So it's the same as it was before. SEM 1 squared plus SEM 2 squared minus 2 times R, your correlation coefficient, times SEM, running out of space, 1 times SEM 2. Running out of space. Basically, it's this, then minus 2R SEM1 SEM2. So that's what you're changing. You're just adding this to your equation for SED. Everything else is exactly the same. Now, technically, this was always there. But if they're independent, if they're not correlated, R was always 0. And if R is 0, then this whole thing is 0. And so it's just this minus 0. So you could always use this equation for every t-test you do. But if they're completely independent, R is 0. So it doesn't really matter. So, in that case, if you have two groups, you would have to find their correlation, or the correlation would be given to you. But we just did correlation, so if you wanted to, you could find that. So you could find at group 1 depression level, you find a z-value. At group 2 depression level, you find z-value. You'd multiply those two z-values, you'd add them all up, divide by number of pairs. In this case, it would be 40. Then you get your R. Plug the R into here, you could do your t-test. So, very, 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 very similar to regular t-test. You're just adding in this one extra part to your equation for SED. So you use it when you have two groups. You only use it when you have two groups. Two groups that you're comparing who have correlated measurements. So in this case, it would be depression. Why are they correlated? Well, in this case, they're correlated because they're the same people. So like if John was one of these college kids, and John always had really high depression, you'd expect, even if his depression went down because of the drug, it would still be relatively high compared to the other kids in the group. Or if Sarah had very low depression at the beginning and took the drug, it would go down, maybe, but you'd always expect it to be lower than the others. So there is a correlation, that there's relationship between the measures in group 1 and the measures in group 2. So that's when you would use a paired samples t-test, and that's how you do a paired samples t-test. All you do is you just add this one little bit. SEM1 and SEM2, those are the same numbers you calculated here, except they're not squared. So if this value was 2 and this value was 4 before you squared it, this would just be 2 and this would just be 4. And then you just plug in your R, your correlation coefficient, minus 2 times all of that. Now conceptually, it's important to note something, which I will tell you once I have space. Because this was on the quiz. I looked at the online quiz today, and some people got this wrong, so I want to point it out. So, or I think the quiz was today. People took the quiz today, so I saw some of these grades. So, your T ratio is this, right? Now, when you have this, minus 2 times something, you're going to be making your SED smaller. So as correlation goes up, SED goes down. as R goes up. The more related your two groups are, the less variance there is in the difference between the two means. So if R is 1, then this is 2 times this. If R is 0.5, then this is 1 times this, right? If R is 0.25, then this is a half times this. So anytime R is around, this is going to make this smaller because you're accounting for some of that variance. So here, this then goes down, and as your denominator gets smaller, your p-value would then get bigger. So consider that. Okay, anyway. I just noticed that was on the quiz. Your t-ratio, which is this number, that gets bigger. As your SCD gets smaller as the correlation goes up. Whoops. So I saw another question come in on the email, so let's check that. Oh, it was walk through Pearsons R. So Leaf Krutko, we did walk through Pearsons R, so I hope that you are cleared up on that. Okay, so I got another question earlier today that was about how to put into words the finding that you wind up finding. So how do you make like a lay person's conclusion to your question? And I think this is, and they said that they also heard other students saying this too. So it seems like it's something that is out there, an issue for people. So I just want to talk about that for a second and try to come up with answers for kind of each type of question. So let's just find one that would be good. Okay, so let's do one for each type of test that we've done. So we have correlation, we have paired samples t-test, I'll just call it PS, paired samples t-test. We have Oneway ANOVA, which again just means you have one IV, and you have factorial ANOVA, factorial, which just means you have 2 or more IVs. So let's say you have a correlation. So R equals 0.8. R squared, which remember is your effect size for this. It says how much of the variance is explained of y by x. So how much variance in y is explained by x. That's just squaring r squared, 0.64. So here you could say, as x, whatever x is, let's say it's height and weight. So as height increases, weight probably increases also. Right? That would be that. As height increases, weight probably increases as well. You could say, after you calculate r squared, you could say that 64% of the variance in weight is explained by height. So that's how you would put the effect size into common language. 0.64 effect size, 0.64 r squared says that 64% of the variability you see in weight is explained by height, by your x. So that's how you would kind of put a correlation into conventional English. What about paired samples t-test? Paired samples t-test is going to be similar to a regular sample t-test in terms of how you explain it. Why is it still in eraser? Because definitely screwed something up. There we go. So this is going to be very similar to Michael. We'll have to know about regression after the test. We're going to do regression, and it won't be too far of a jump away from ANOVA, because ANOVA is just a different type of regression. But we'll do regression after the second midterm. So here, let's say you find a t-value that's significant. So like t equals 6.8. That's a big p-value. So here you could say, so let's say you're testing two groups, like men and women on IQ. So here you could say that, and you found that women scored higher, their mean was higher on IQ than men, and you compared that, you found a significant t-value. You would say, t at degrees of freedom of whatever you have equals 6.8. Women probably have a higher IQ than men. So that's how you would write that. So you were measuring IQ. Women's mean was like 120. Men's mean was like 110. You compared those means in a t-test. The t-test was significant, and you write it out like this. Or it could be, time 1 and time 2 on depression. So you could say, people measured at time 2 probably have lower depression than people in time 1, which was before drug delivery. So that would just be that. Okay, one-way ANOVA and two-way ANOVA. So remember, a one-way ANOVA usually has 3 or more groups. If you have 2 groups, it would give you the same result as a t-test. So I'll just consider it as having 3 or more groups. 3 plus groups. Now you could do it, you really could do an ANOVA with 2 groups, but you're going to write it out similar to a t-test because you're just comparing 2 groups against each other. Here you have 3 groups or more. Let's say you get an F value, and it's 22, it's some big F value, and you're testing height, 1st grade, 2nd grade, 8th grade, like earlier, on height. So here you would say, you would do your F test. You would say, so first you would say, once you find it significant, you would say, there are, you would say like there are probably differences in height across grades. So that's just your F statistic is significant. Then you do your Tukey's test. You get your unsignificant difference. You compare the means of the 3 groups against each other, and then you could say, you could say like 8th graders probably taller than 1st and 2nd. First and 2nd, probably not different. right? So if your Tukey's test gave you a number that was bigger than the difference between the means of first and second graders, then you would say that they're probably not different. And for factorial ANOVA, factorial ANOVA would be the same thing. You just have to do it per IV that was statistically significant. So it would be the same kind of description based on the number of groups. But remember, in factorial ANOVA, you would have like no drug, some, and a lot. And then maybe here you have men and women. And so in your factorial ANOVA, if this is significant, so if this is significant, so like for F value, your F test for this was significant, you would explain it like this. If this was significant, you would explain it like that. If the interaction is significant, then that is a new thing. And you'd want to say something like, so if like sex times drug is significant, then you'd want to say something like the effect of drug is probably dependent on sex. Then you could say like you could then say like no difference. Yes, I'll go over that in one sec. No difference. Well, no. Since this is two levels, you wouldn't have to say anything else. So that's if the interaction is significant. Something like that. Because that says at certain levels of one IV, you get an effect of other levels of the other IV. So think about things like that when you are putting your findings into common language. Okay, so I'll erase from this side so you have time to look at it. You can always pause after watching this again. And now I'll go over the conceptual aspects of all the different variants in ANOVA. So it's all variants. Analysis of variance, it's all variants. It's like the really short answer, but okay, so I like this magenta, so I'll keep using it. Let's imagine you have a straight line. Let's imagine this is a straight line and its height. And we're testing our 8th graders again and our 1st and 2nd graders. Look at that. That. Also imagine these are all the same size because they should be. So we'll say this is 1st grade, this is 2nd grade, and this is 8th grade. And these are distributions of height. So remember, these are distributions. Each one has a mean and standard deviation. So this has a mean, and it has a standard deviation. This one has a mean and standard deviation, and this one has a mean and standard deviation. Okay. Now, if you consider all of them, all the scores together, somewhere, probably around here, there's an arrow, you have a grand mean. So the grand mean is the mean of all the observations together. So 1st graders, 2nd graders, 8th graders, you lump them all into one group, you take the average, you get a grand mean. That's important. So, sum of squares between and sum of squares within. Sum of squares within is describing the amount of variance in each group. So this amount of this variance. How much do scores vary in each group? Now, there's a way of calculating it that you don't have to worry about because Dr. Kiliansky just said you don't have to worry about it. So this is sum of squares within. Now, remember I said assume that all of these are the same shape and I'm just a crappy Girard? That's because there's only one sum of squares within, right? You only calculated once. Because an assumption of ANOVA is that they have the same variance. It's called homoscedasticity. It's the assumption that your groups all have the same variance. So all three of these like brackets that I'm making should all be the same size. And this is all sum of squares within. How much variance is there within the group distributions? So first grade, second grade, eighth grade. Sum of squares between, another color, is how much variance is there from the grand mean to each other mean. So like from first grade to here, from second grade to here, and from eighth grade to here. So how much of this, how fat is this curve? You can imagine there being one grand curve. Right? One big distribution that centers on the grand mean. I didn't really draw it very well. But you can imagine that there's one distribution of all the scores around which surrounds the grand mean. So how much variance is there between your groups and the grand mean? And that's sum of squares between. So that's between your groups and the grand mean. Within is sum of squares within your groups. And between is between your groups. So what you're doing is you're measuring the fatness of these distributions against the fatness of this distribution, the grand distribution, the grand mean, and the distribution of scores around that. So this is like the more important part, I think. Mean square between and mean square within, they're just adjusting for your sample size and for the amount of groups that you have. So you're just adjusting it relative to your degrees of freedom. So, but it also mean square within just equals sum of squares within divided by degrees of freedom within, right? And then mean square between equals sum of squares between divided by degrees of freedom between. So if these were both 1, then your mean square within just equals your sum of squares within, and your mean square between equals your sum of squares between. So this just what's the right word? You're just kind of transforming your sum of squares between into some new number based on your degrees of freedom. So mean square within and mean square between, they're also just describing the variance that exists both within your groups and from your groups to your grand mean. So you can still think of them as measurements of variance. So your fraction of f equals mean square between divided by mean square within, what this is basically just looking for is the amount of space that your groups exist in. So like the plane that your means exist in, this whole space, is it sufficiently big enough to allow your groups to exist with whatever fatness of distribution they have and still see a difference? So like if first, second, and eighth grade are all next to each other, mean square between would be very small. And conversely, mean square within would be quite large, because if these 3 fat distributions all lived next to each other in one closed off little space, then this would be a small number. But since you have the 8th graders out here, what's happening? Something's going on with my mouse. Since you have the 8th graders out here, they're making the mean square between much bigger because they are kind of widening the area with which these distributions have to live on. So they're all the way out here. They're making the plane that they exist on much longer, which makes a much bigger mean square between. Now, if the distributions were really, really fat, if they had very high standard deviations, then the mean square within could counteract that, and you would have kind of them all overlapping each other. But that's not the case here. So here, you see that you have a big mean square. Well, Siri thinks I'm talking to her. Here, you have a big amount of mean square between. You have a big amount of variation from your means of each individual group to your grand mean, that's what you're measuring, and a relatively small mean square within. These distributions are pretty thin. You have a lot of empty space between them. You have pretty thin distributions. So this is pretty small, this is pretty big, and in this fraction, that would give you a pretty high f. Or, depending on what these numbers are, the f would be big. If this is big and that's small, so if this is big and that's small, then your f is going to be big. So, and then sum of squares total, that's mostly just used to calculate your effect size. Sum of squares total is just the addition of the sum of squares between and the sum of squares within. That's to calculate eta squared. So that's just the amount of variation there is from groups to grand mean plus the amount of variation within the group. It's not as easy to describe visually. It's just the addition of those two things to kind of give you the total amount of variance in all the pieces that are operating. I hope that makes sense. But that's where it comes from. Think about how much space these distributions have and how much each distribution takes up. If they're all fat, then they could be on a big plane and they would still not be different from each other because they're all overlapping. Okay, so with that, I'm going to end it there. It's been an hour and 5 minutes. So hopefully I answered all your questions. If I didn't, please do email me. I will see you on Tuesday for the first part of the exam. We can also talk after the conceptual if you still have problems or questions relating to the computational. Remember that you can have bring your textbook to the computational. You can have your formula sheet for the computational, and then I think you'll be good from there. So shoot me an email if you have more questions, and I will see you on Tuesday. So good luck with your studying, and please do reach out to me if you have additional questions.